In this skill, we're going to be thinking about Gibbs free energy and the equilibrium constant and how they are linked together. And we're also going to be thinking about how we can use the Gibbs free energy, the equilibrium constant, and knowledge about the activation energy to figure out which direction a reaction will proceed and at what speed. Let's start by setting up a table to explain how Gibbs free energy and equilibrium constant are related. If we have a reaction where our delta G is less than 0, we know this is a reaction that is spontaneous in the forwards direction. So that reaction will happen in the forwards direction. This is telling us that our products will be favored equilibrium, which means our equilibrium constant K must be greater than 1. If, on the other hand, we have a delta G naught that is greater than 0, that's telling us our reaction will not proceed in the forwards direction. Instead, it's going to proceed in the backwards direction. That means our reactants are favored at equilibrium, which means our K must be less than 1. Finally, if we have a situation where delta G naught is equal to 0, that means we're at equilibrium. So our reaction will neither happen in the forwards or backwards direction because we're at equilibrium. And we know that at equilibrium, our equilibrium constant K is equal to 1. The other thing we need to think about is the activation energy. Now, activation energy doesn't affect the direction that the reaction will happen. That is determined by the Gibbs free energy and the equilibrium constant. However, activation energy does determine the speed at which a reaction happens. If we have a high activation energy, the higher our activation energy, the smaller the proportion of particles that are going to have enough energy during a collision to meet the activation energy and actually react. So a high activation energy means a slower reaction. However, a low activation energy, that means that we have a greater proportion of particles that have enough energy in a collision to overcome that activation energy, and therefore a higher proportion of particles that will react and a faster reaction happening. So it's important to remember the change in Gibbs free energy and equilibrium constant, those determine the direction of the reaction, but the activation energy, that determines the speed. Okay, so let's try this question. In this question, a scientist wants to predict the equilibrium position and rate for a reaction that has a negative change in Gibbs free energy in the forwards direction at 273 Kelvin. We're also told this reaction has a low activation energy in the forwards direction and a high activation energy in the backwards direction. Okay, so let's start by thinking about Gibbs free energy. Now, we were told in the question it has a negative change in Gibbs free energy. That means our change in Gibbs free energy is going to be less than 0, since it's negative. So we can fill that in here. Delta G naught is less than 0. And we know that delta G naught being less than 0 means our reaction is thermodynamically favorable. So it's going to be favorable. So what this means is that our forwards reaction is happening. And it means our products are going to be favored at equilibrium, and K is greater than 1. So thinking about our equilibrium constant now, K is going to be greater than 1, and we're going to have our products favored at equilibrium. So we have our forwards direction happening. So now we need to think about the activation energy in the favored direction. We know the forwards direction is favored, and we're told we have a low activation energy in the forwards direction. If we have a low activation energy, that means we're having a faster reaction occurring. So the activation energy is low in the forwards direction, so the reaction will progress quickly in the forwards direction. Let's do one more question of this type. In this question, we're again trying to predict the equilibrium position and rate for a reaction. This time we're told it has a positive change in Gibbs free energy in the forwards direction at 273 Kelvin. We're told it has a high activation energy in both the forwards and backwards directions. So we've been told it has positive change in Gibbs free energy. That means delta G naught is greater than 0. In other words, our forwards reaction is not thermodynamically favorable. So our delta G naught is greater than 0, and our reaction is unfavorable at 273 Kelvin. What that means is that instead of our forwards reaction happening, because it's unfavorable, our backwards reaction is going to happen because the backwards will be favorable. And that means that our equilibrium constant K will be less than 1, meaning that our reactants are favored at equilibrium. So our equilibrium constant is less than 1, and our reactants are favored in equilibrium. Finally, we need to think about the activation energy and how the reaction will progress. Well, we know we're talking about the backwards direction. We were told here the reaction has a high activation energy in both the forwards and backwards directions. So if we have a high activation energy in the backwards direction, and that is the direction our reaction is going, our high activation energy means a slower reaction. So we have a high activation energy, and therefore our reaction will progress slowly, and we know it's going to happen in the backwards direction. So in this skill, first we need to look at the change in Gibbs free energy. If it's less than 0, our reaction is thermodynamically favorable and it will happen in the forwards direction. If it's greater than 0, our reaction is thermodynamically unfavorable and it's going to happen in the backwards direction instead. If we have a forwards reaction happening, we know K must be greater than 1 and our products will be favored equilibrium. If we have a backwards reaction happening, we know that K must be less than 1 and our reactants are favored equilibrium. Finally, the activation energy doesn't affect the direction of the reaction, but it does affect the speed. So once you know which direction the reaction is happening in, figure out if the activation energy is high or low in that direction. If it's high, we're going to have a slower reaction, and if it's low, we're going to have a faster reaction.